Hello, welcome to everyone in this video. This is lecture number 8 on solid state physics. Today we want to discuss about the magnetic property of matter, that is the dia, para, ferri, ferromagnetic material, then classical Langevin's theory via dia and paramagnetic domains, then quantum mechanical treatment on paramagnetism is in partition function, and then Curie's law. Okay. So you can see this is the syllabus of University of Calcutta 6th semester physics honors. This crystal structure, elementary lattice dynamic, these two parts already covered in the previous lectures. Today we want to discuss about this portion, that is the dia, para, ferri, ferromagnetic material, classical Langevin theory of dia and paramagnetic domains, quantum mechanical treatment, paramagnetism, and then Curie's law. Up to this portion we want to discuss, and in then upcoming session we will be cover up this upcoming portion, right? So let's start today's discussion. At the first, what do you mean by paramagnetic material? Actually, you know very well that is in the atom there is a nucleus. There is a nucleus where the proton and neutron, that is the proton and neutron are within nucleus, and the electrons moves around this nucleus. Electrons around this nucleus, right? So this electron motion is like that. Then there is a current in the opposite direction because the charge of the electron in the opposite. So this current makes a magnetic field, because you know the moment magnetic moment is nothing but current into cross section area Ia. So due to motion of electron or charged particle, there is produced a current, and this current produce the magnetic moment. So that is the magnetic material, that is the origin of the magnetic material. So this magnetism within the solid, that is the magnetic property arise within the solid due to what is the main effect? Spin of electron, that is the spinning property, or orbital motion of electron, that is the orbital motion of electron, and the spin of nuclei. So these three factor causes the magnetic property within solid. I think clear why the magnetic property arise within solid. These three main factor arises magnetic property within the solid. Clear? Depending upon the solid, this property will be different. That means the material or the solid material known in the different name. First one, when the susceptibility. What do you mean by susceptibility? That means suppose you have a magnetic material. Suppose you have a magnetic material, and if you apply this external magnetic field, this is north pole, this is south pole, this is external magnetic field. So there is the dipoles, you know, the magnetic moment or dipole moment is Ia, that is this produce a teeny dipole, right? So these teeny dipoles are aligned in along the field or opposite to the field depending upon the material's property. So this dipoles moment aligned per unit volume is known as the magnetism. M is the magnetism, capital M is the magnetism, and H is the field. Capital is the magnetism. Magnetism means the dipole's moment aligned per unit volume. Dipole moment aligned per the unit volume is known as the magnetism, and H is the external field. So this magnetism actually proportional to the external field. If you apply the more field, then the material will be more magnetized, and after a certain part this will be saturation. Okay. So this proportional constant known as the susceptibility, this is the properties of the material. This susceptibility will be negative, that means the magnetism is opposite to the applied field, and the value is less than 1, then property, this material is known as the diamagnetic. So when the material shows these two property, this property actually chi less than 0, and the value of the mod of chi, that's the susceptibility, is very much less than 1, then the material is known as the diamagnetic material. For example, bismuth is the example of the diamagnetic material. Then another category of the material is the chi is greater than 0, that is the positive, but the value magnitude of this chi is very much less than 1. So these both case the value is very much less than 1, but one is positive, one is negative. For negative this is diamagnetic, for positive this is paramagnetic. For example, aluminium. And the third category, which when this is positive and the value of chi is very much greater than 1, that means we apply a small field, external field, the magnetism is very high. That means with a given small field, the magnet property will be aligned along this applied field, right? These are known as the ferromagnetic material, and these ferromagnetic material are subcategories into three parts. That is the normal ferromagnetic material, anti-ferromagnetic material, ferrimagnetic material. Ferromagnetic material, why there is a permanent dipole moment. In these two cases, there is no permanent dipole moment. For diamagnetic, dipole moments align in the opposite of applied field. For paramagnetic, dipole moment align along the applied field. And for ferromagnetic material, there is a permanent dipole moment. That means without external field, there present a dipole moment. And these ferromagnetic material are subcategories as the normal ferromagnetic material when the all dipoles align in the same direction. Antiferromagnetic, that is the one layer is aligned along one direction, and the next one layer align in the opposite direction. Okay, so this is the antiferromagnetic, and there is the same as the antiferromagnetic ferromagnetic, but there is magnitude of the dipole is different. Okay, magnitude of the dipole is different. You can see this layer and this layer is opposite, but the magnitude of this layer of dipole is different, but here this is same. So net is 0, but their net is not equal to 0. For ferromagnetic material, example is iron, nickel, cobalt. For antiferromagnetic material, example is chromium, nickel oxide. For ferrimagnetic material, nickel ferrite, etc. So I think clear about the magnetic materials. That is, these types of magnetic materials available, and why this is arises due to the internal structure which causes the magnetic moment due to motion of the electron and the nuclei spin. Okay, so I think clear about the question. If there is any doubt, you must comment in the comment box. Next, you can just see this variation for dia this is negative. That is, if you apply the magnetic field, the magnetic materials, magnetic dipole are opposite. That's why this is negative. For para and for antiferromagnetic, this will be like that. For ferro and ferrimagnetic, for antiferro, this net is 0. That's why this nature. For ferromagnetic and for ferrimagnetic will be like that. So I think clear the nature of the applied field with the magnetism will be like that for different material. Now comes into the diamagnetic material. Diamagnetic materials is like that when if you apply metals within this magnetic field, this is north pole, south pole, and this is a magnetic field, then these lines of magnetic fields are repelled, slightly repelled by this material, by this diamagnetic material. Okay, so the chi, this is susceptibility less than 0. Chi is independent on temperature, that is no Curie temperature, and value of chi is like that, and mu, that is the relative permeability, will be like that, less than 1. The magnetic lines of force repel slightly. So this is the basic property of diamagnetic material. This this property explained by Langevin's theory of the diamagnetic domain. Okay, for Langevin's theory, there is make some certain assumption. What are the assumption? That is mu, that is the relative permittivity does not change by external environment. Due to external environment, mu is not changes. This is the assumption. Next is no mutual interaction. That is the dipoles are independent to each other. Third is they only interact with the external magnetic field. That is the dipoles interact only due to presence of external magnetic field. Then they can orient along any direction. It's possible to oriented any direction, that is a continuous, and without external field they are complete random and thermally hesitate, so that there is no net magnetic moment. So in case of diamagnetic material, the net magnetic moment without external field is 0. Okay, Now you can take that is the electron revolves around the nucleus in a circular orbit. So this is a nucleus. This is a nucleus, proton, nuclear, neutron, and this electron moves in the circular path. So if you take rho is the radius of this path and m is the mass of this electron, then you can easily write down this relation, that is the m omega naught square rho, that is the velocity, and this is the Coulomb force, that is Z E into E, because in this nucleus this charge will be Z E and this is the E. So Z E into E 4 pi 4 pi epsilon naught rho square. Okay. So finally you obtain the velocity of the revolution velocity of this electron will be like that. In presence of the magnetic field, the Lorentz force on the electron moving with the velocity v. The Lorentz force will be like that, E v cross b, that is E rho w, that is v is nothing but rho into omega. Omega is the angular velocity, v is the linear velocity. Then net force is nothing but the nucleus force plus the centrifugal force equal to like that m omega square rho. So finally obtain this relation, and after calculating the omega, the angular velocity of the particle will be like that. This is known as Lemma theorem. This plus for parallel and this anti-parallel. Now the frequency change. This is the angular frequency. So this linear frequency is like that. So this is the additional. So angular, if you divide it by 2 pi, this will be the linear frequency. So this is the additional frequency arises here. So due to this change of frequency, current is will be altered. When the frequency is changed, the current will be changed. So there is a alternation magnetic field. So this current is nothing but charge into additional frequency, because you know current equals to charge by time, and 1 by time is nothing but the frequency. So this is minus e and that one. So you will be obtain this expression. So magnetic moment mu e is nothing but current into area Ia. So put this value of current and area is like that. So finally obtain the magnetic moment is this, and here the negative sign says that the opposite of this field, induced magnetic field opposite to this field, and this is the property of diamagnetic material. If atom contain Z at electron, the total induced magnetic moment will be like that, because for single this one, so for Z number electron like that. So if field along the Z direction rho square equal to this radius is mod of x square plus mod of y square. That is the mean square of perpendicular distance from the axis. And you know r square is addition of these two things, and for spherical symmetry they are equal. So r square is 3 by 2 rho square. So if you put these things, you will be obtain this expression, that is the magnetic moment. For solid containing n atom, this magnetic moment per unit volume is nothing but the m, and then divided by h, you will be obtain the susceptibility. So this is the susceptibility. I think clear, and you do this calculation step by step. I think you easily understand this portion what actually happened by mathematically. So chi is independent of temperature. You can see there is no expression of temperature. So you can see this is independent temperature. So in temperature variation, the chi will be like that, constant. Next thing is classical Langevin theory for paramagnetic domain. The previous one is the diamagnetic domain. This now is the paramagnetic domain. Okay. Actually, in this atom, the permanent magnet dipole moment, there is a permanent dipole moment, but the in the absence of the magnetic field, the total dipole moment, that is will be zero. They are randomly oriented. That's why the total magnetic moment will be zero. But when you apply the magnetic field, external magnetic field, the dipoles are oriented along that, and they makes some magnetism. See, this susceptibility is small, positive, and temperature dependent. The actually in this material paramagnetism actually happening. Some metal atoms nucleus having no odd number of electron, oxygen molecule, free atom, and having ion having a partially filled inner shell, example rare earth, actinate element ions. So this is a material where the paramagnetism actually arises. Okay. Now, if we consider, because there is a permanent magnetic moment, this permanent magnetic moment makes angle theta with the applied magnetic field. With the applied magnetic field. With the applied magnetic field. So, E equals to minus mu dot B. The energy equals to dipole moment into magnetic field. So, this is minus mu B cos theta. Now, if you take the Maxwell-Boltzmann contribution, the exponential proportion will be like that. And now take this portion, sorry, theta to theta plus d theta. So number of atom that within this span will be like that. Now from the Maxwell-Boltzmann distribution, if you take the average value, will be like that. That is mu cos theta dn equals to n mu cos theta dn by dn. Put this value of dn will be like that. That is mu n is equal to this one. I think you can do this calculation. Just take this. This is as a x, that is mu b by kt, and cos theta equal to y. So this is cos theta is y, and this one, and dy is nothing but minus sin theta d theta. And actually, in both case, this is minus cancel out, and if you put this limit, that is cos 0 is 1 and cos pi is minus 1. That's why the limit 1 to minus 1. Okay. If you partially integrate, partially bypass, integration bypass, and put this value, you can easily find out this expression. Okay. Do this calculation along this path, you will be obtain this expression. And this is nothing but cot hyperbolic x, because cot hyperbolic x is cos by hyperbolic x by sin hyperbolic x. This is cos hyperbolic, this is sin hyperbolic x. Okay. So do this calculation in your own hand, you can easily find out this expression along this path. And this is known as the Langevin function. This is known as the Langevin function. If you draw this Langevin function like that, actually this total curve will be like that. This is the positive saturation, this is the negative saturation. Okay, this is the Langevin function. And you need to care about, that is when Langevin function is tends to 0, this slope will be x by 3. Okay, this slope will be x by 3. Nothing but you just take this calculation. So m will be like that, and then susceptibility will be like that. This is nothing but c by t. So there is a dependency on temperature, and this is known as Curie's law. And here you just express this one, and for high temperature, here you can see that is the ordinary temperature. High temperature, for high temperature, if you calculating this thing, binomial theorem, and just neglecting the higher order of x, because this x is mu b by kt. If t is high, then this is neglected, so you can easily find out this one. So I think you can do this calculation step by step. You can arrange these things. For low temperature, x is very large, so this will be n mu with the saturation. Okay. So at absolute zero temperature, all dipoles along the magnetic field within a saturation of magnetization. That is when there is a temperature is tends to 0, that is the absolute scale. Dipoles are oriented along this applied magnetic field, and this gives the saturation. And this at zero temperature, no thermal agitation. So due to external magnetic field, all dipoles must oriented towards the external field. This is called as the saturation. Now comes into the quantum mechanical treatment of paramagnetism. In classical theory, we just take the value of energies along all possible direction. That is this. If we take this magnetic field, and this is the mu, this theta is continuous. We take this theta is continuous in case of classical Langevin theorem. But you know from the atomic physics, this dipole moment oriented in a specific direction, some specified direction. So there is a anomaly arise due to atomic physics and the Langevin theorem. That's why we take the quantum treatment, that is, we take the discrete orientation of the dipole moment with the external magnetic field. Okay, so this is the difference between the classical and the quantum quantum situation. So mu parallel, which is from parallel to the magnetic field, is nothing but G mu V mj. This is actually obtained from the atomic physics. So in your previous semester, I think you know about the atomic physics this relation. And this parallel apply to the magnetic field. G is the Landau factor, whose expression will be like that. And this is 2 for net analysis moment of dipole due to electron spin, and this is for orbital only. So I think you know this all about obtained from the atomic physics. And if you take this average value, just taking the average into electronic portion of the Maxwell distribution, and if you take this G mu V B by KT is alpha, so you can simplify it like that. Okay, and for high temperature, this tends to 0 and this is tends to 0. Okay, because their T is in the denominator. So exponential alpha mg is nothing but 1 plus alpha mg, neglecting higher order because this is very small. So you put this expression, you will be obtain this one. And the summation of mj is nothing but this is 0, whereas positive and negative are cancelled out to each other. If you summation minus 1 to 1, it will be 2j plus 1 because 2j plus 1 number of term here. And summation of mj square is nothing but 2 into 0 to mj square. So this is this one. So if you put this expression, you will be obtain this simplified expression and put this value of alpha, you will be obtain these things. And this is nothing but similar to like classical Langevin theorem. Okay. So finally obtain these things, and at low temperature, this is this is similar to this Langevin theorem. At the low temperature, alpha is large. So if you take these things, and this is nothing but ln this one, and this is known as the partition function. If you calculated this partition function very carefully, you just take into account this separation. Uh, and common out, you will be obtain this GP series. Summation of GP series will be like that, and then rearranging them such that you can write sine hyperbolic. These are sine hyperbolic. Okay, there is also hyperbolic. There is also sine hyperbolic alpha by 2. There is also sine hyperbolic. So average value will be like that. There is sine hyperbolic alpha by 2. So if you separate out this thing and ln property and then taking the derivative and rearranging the, you will be obtain this expression. This is known as Boolean function, which is 1 for x tends to infinity, and for minus 1 this is minus infinity. So if you draw this Boolean function, will be like that. Finally you will obtain these things. For high temperature x tends to 0, you will obtain this same things as Langevin theorem. So this also satisfy this high temperature property. Okay, Langevin theorem satisfy here also. So this is your question. You must attend this question, right? So I think clear about all these things, and you just make your notes with this expression. If there is any doubt, any confliction, you must comment in the comment box, right? So this is all about me. This is my contact detail. You can connect with this Telegram channel. This is my YouTube channel details. Go to this channel. You will get different physics related videos, some mathematics. Like this session if you learn something from this session. Share this video to your friends. Either he or she also get benefit from this video. Subscribe this channel if you need this channel. Those already subscribed, thanks for subscribing. Press the bell icon to get notification of upcoming video. So take care. We'll meet in the next video as soon as possible. Thank you.